Hi guys, welcome to today's tutorial. We are going to look at some titration curve calculations. This is probably the one of the most difficult section in this particular achievement standard, and if you're someone that's doing med school at Auckland Uni or something that hasn't done a quiz because you did Cambridge IB, this hopefully would help you as well. Okay, so this is going to be a two-parter as well. So this is going to be part one. I'm just going to go through the really simple example, and I'll go run through every single possible points that you need to calculate alongside the titration curve. So what is a titration curve? I mean, a titration curve, hopefully you all have done, still remember your titration experiments from year 12s, because what titration is that and we're still looking at acids and bases titration. So we do a titration when and then there will be a color change when the acid and base completely neutralize each other, and you just add in that one extra drop of acid or base depending on what's in the burette, then boom, you have a color change. That's when you know your titration is finished. So we can actually plot a titration curve graph, a titration curve to display the changes of the pH as we do the titration. So that's what titration curve is about. So it's almost like if you were doing the titration experiment, as you're dropping down the base, for example, from the burette, and then as one drop of it goes inside, the pH of the solution will change, and you can actually calculate the pH of that solution at any time of the titration process. So, but there, we don't need to do that. There are normally about 4 to 5 different we're going through a lot down this talking about location of interest. On the titration curve, we have about 5 pHs of interest. You can think of it like that. Okay, so I have an example question with you today, and we are going to go through this particular section. Hopefully you can always, the beauty of YouTube is that you can always watch again and again if you don't get anything. But here's a really simple question. If I have, and I just got straight to the point, I didn't mention anything about what's in the pipette, what's in the burette. You're not required to know that, but you should know that 15 mils of 0.1 mole per liter CH3 and H2, so that must be in the pipette, because and then that's in the flask, and you're putting HCl into the flask. So you can think of it like, say this is your flask, and then this is your flask, and then you're just adding in HCl drop by drop, and then you're trying to have a look at the pH change as this HCl is being added in. And then we gave you the pKa because we're gonna need all the numbers. Now, something I did forget to remind you guys is that in chemistry, every single number that we give you tend to be used at least once, and normally most of the time you only need to use it once. So we don't give you numbers for no reason. Okay, so unless in this particular case I could also give you the Ka of this number, so I could give you Ka of CH3 and H3 plus, which is just you can transfer that between the two values, which are exactly the same thing. So I'm just trying to move my chair. Okay, so let's now we understand the context. Let's have a look at what we're actually looking at. Okay, so first thing first, let's look at the initial pH. So what does this initial pH mean? So this means this is before, in this particular case, this is just looking at the pH. This is looking at the pH of what is in the flask before titration even began. Before titration even started. Okay, so this is, you need to think about what's in the flask, and this is where you need to remember in your year 12 titration, you can't, the one with the certain mils is always obviously the one that you accurately measure out from the pipette, so that goes in the flask. So in this case, in this particular question, I'm just calculating the pH. The question is literally asking you, what is the pH? What is the pH of CH3 and H2? That's all it is asking. And then this is where you need to remember the equation that you got from previous lessons. We gave you the pKa, which is CH3NH3 plus, we want you to calculate the pH of CH3NH2 because that's in the flask and we didn't add any HCl in yet. We just want you to calculate that pH. So you should be able to identify, oh, look at that, this is the acid, this is the base. So we are just doing a weak base pH calculation. Okay, and then you just need to remember the equation, which is H3O plus equals the square root of Ka times Kw divided by the concentration of the base. So in this case, which is going to be, what's Ka? Well, we know pKa. Ka is just going to be 10 to the power of negative 10.64 times 1 times 10 to the power of negative 14 divided by the concentration of the base, which is 0.1. Okay, so I'm just going to quickly run these numbers in my calculator. I haven't done these questions beforehand. 10.64 and then times 1 times 10 to the power of negative 14 divided by 0.1. Then we square root this bad boy. So we get 1.51 times 10 to the power of negative 12 moles per liter. And we want to find the pH. pH is negative log, whatever that is. So this is why I said that it is absolutely essential that you know what we're doing beforehand. So the pH is 11.8. And this is actually quite good. So you need to remember that we calculate the pH of a weak base. So 11.2 seems about right. And that's the first part. So that just means before we even started doing the titration, you can already determine the pH of the solution that's in your flask. When you got 15 mils of that 0.1 mole per liter of CH3NH2, chuck that in the flask and you already know the pH, which is 11.8. Okay, so that's the first part. So the initial pH, you just need to think about what is in the flask, what came out of the pipette, and how do you know that? It's always the one that have been given the mils, the one that's always been given the volume, and that's going to be your substance of interest, and then you are going to turn that, you're going to find that pH of that substance, and you just literally do what we did in previous lessons. Just determine what type of, is this an acid or base calculation? Yep, it's a weak base, boom, chuck the equation and substitute numbers in, and then you get a very easy tick there. Okay, now next one, pH halfway to equivalence point. Now I do want to just quickly talk about what equivalence point means. Equivalence point, now I mentioned this later as well, but equivalence point is when the mole of the acid equals the mole of the base, because that's what equivalent means, doesn't it? Yeah, so because you have completely neutralized each other and you don't have any more of it. Okay, so what it means by halfway to equivalence point, this means in this case we have, let's look at this equation first. We have CH3NH2 and we're dripping in HCl from the burette. This is going to neutralize each other. I'm going to make the conjugate acid of CH3NH3 plus and Cl minus. Okay, so this is going to be the equation. Now hopefully that's not too hard to write from your perspective. Okay, so what's going to happen here is that I have lots of this at the beginning and I'm dripping in the HCl as we speak. So at halfway to equivalence point in this particular context, in this particular experiment, it means I have added enough HCl and neutralized half of CH3NH2. Okay, so you don't, in this particular question, there's actually no calculation involved, but you need to understand what we're looking at here, because they always just ask you the question, there's no calculations required, but you need to explain to us what's happening here. Okay, so at halfway to equivalence point is that we added enough HCl and we neutralized half of the CH3NH2. So what does that mean? That means the mole of CH3NH2 is going to be twice as big as the mole of HCl. Okay, so the mole of HCl, so in this case, let's just write this equation again. I'm just going to use X to do these, because this is only part one. I can obviously make this a lot more difficult if I want to, but I'm just hopefully not trying to scare you off too much. So if what it means by halfway to equivalence point, if this is X, this is going to be 2X. Okay, and what it means is that I've added, again, go back to the definition, go back to here. I've added enough X, I've added enough HCl, and I neutralized half of the CH3 and H2. So what happens here is that this will be gone, and I've neutralized half of it, so it's down to X, 2X. 2x minus x equals x, and this is 0. I don't have any more of it left. What did I react? What did I produce? I'll make x moles of this, and I'll make x moles of this. And this one I don't really care about because I Cl minus is suspected. I don't really care. Now, can you see I have produced, if you excuse the rain, just pouring down the rain, but CH3, can you see the CH3 NH2 mole equals to the mole of CH3 NH3 plus? Oops, why is that just rectangle? These two concentrations, these two moles are exactly the same. Why is that again? Because I've added enough HCl, I neutralized half of the CH3 NH2, so it has, 0.5 or half of the original thing remaining, and I produced equal amount of the conjugate acid. So the mole is going to be the same. If the mole is going to be the same, and then hopefully you can see that I have this guy and I have this guy, this is the base, this is the conjugate weak acid, this is a weak base, you have a buffer. Okay, and this is, again, if you're not getting this, go back to the buffer video and look at. This is one of the methods that I emphasize. I'm pretty sure it's buffer video number 2. When you add a strong acid to a weak base, and you only need to add a small amount of the strong acid, you will produce the conjugate weak acid of the base, and then you have a buffer. Okay. Now, how do we calculate the buffer pH again? The buffer pH is calculated as pH equals pKa plus log base over acid. Now again, we talked about this before. When the two moles are the same, this just means pH equals pKa plus 1, log 1, and then which means log 1 is 0, which means pH equals pKa. So that's why no equation is required, no calculation is required. Where's our pKa again? pKa was 10.64. So the pH at halfway to equivalence point, this is where pH equals pKa, which equals 10.64. There's no calculation involved. You do not need to do it, but you do need to understand what has happened. Is that halfway to equivalence point, you added half the amount of the original moles compared to the original moles of the starting moles of the CH3 and H2 in this example. You neutralized half of it. You produced the equal amount of the conjugate acid. You have the weak base, weak acid, buffer. How do we calculate buffer? You use this particular equation, but then these two concentrations are going to be the same because they are equal molars, and then pH equals pKa. Okay, so that's no calculation involved. All right. Now, next part. Now, hopefully that makes sense. Now, next part, 6 mils of HCl was added into the equation. Now, I've always, if they don't give you the equation, I'm always a strong advocate that you can write these yourself, because if you can write these yourself, this is not hard, just a neutralization reaction. Some of my E11s can do this comfortably. You guys should be able to do it as well. But what happens here is that I want you to, again, this is part of the video that we did before. When you add 6 mils of HCl, remember we had 15 mils of, it's 0.1 mole per liter CH3 and H2, that's just in the question. We're adding 6 mils of 0.1 mole per liter HCl. You can see that it's going to neutralize, aren't they? So we are going to look at, this is essentially a buffer pH calculation. Because you're adding a small amount of HCl, you are going to neutralize a small amount of the CH3NH2. In the process, you're going to produce some CH3NH3+. Now, when you have these two suckers mixing together, you have a buffer. And then that's how you can, yep, I need to use the buffer pH. Now, what are we going to do here? I would like you to, especially those in my class, to strictly follow this method, because that means, I don't get 95% plus achievement rate in the standard for no reason, because, there is I found a very systematic way that if you just follow the method, you will do quite well. So here it goes. So what is the original concentration? The original concentration 0.1 moles per liter for this guy is in the question. What is the original volume, which is 15 mils, which is 0.015 liters? What can I figure out? I can figure out, so if you've seen my buffer video before, this should be no news. N equals CV, which equals to 0.1 times 0.015, which means 0.0015 moles. Okay, now let's look at HCl. HCl, the mole is going to be, the concentration is the same, 0.1 mole per liter. The volume is 6 mils, which is going to be 0.006 liters. So the mole is going to be 0.0006 moles. Okay, so this is before anything has happened. So what it means is that I had this, the CH3NH2, I have this many moles sitting in the flask, waiting for something to happen. Then I added 0.006 moles by adding 6 mils of this HCl into the solution. And what has happened afterwards? Well, after, it just means they neutralize each other. So that means the 0.0015 is going to send out equal amount to neutralize this 0.006. I'm going to have 0.009 moles, 0.009 moles per liter left, moles left. All right, because it's a 1-to-1 mole ratio, and this is going to be 0. And what did that become? This becomes, what has that become? This has made 0.006 mole of this. Okay, because if you think about it, this is it takes 1 mole of that to react with 1 mole of that to make 1 mole of that. Yeah, so I have used 0.006 moles, I will produce 0.606 moles of that, and then I had the 0.0015 at the beginning. I spent this many to neutralize the HCl, I have this many left. Now you can have a buffer solution, so you can just now straight away go to your buffer pH calculation. You can just go pH, yep, I have a buffer right now, pH equals pKa plus log base over acid, and you just need to go, all right, which one's the base? This is the base, and this is the acid, and that's how you can figure it out. Okay, again, how is this one the base? This has less H. The one less H is the base. So what's the pKa again? pKa I think was 10 point, what was that? I need to write this number down somewhere, otherwise it's going to keep scrolling up. 10.64. So the pKa is going to be 10.64 plus log base 0.0009 divided by 0.0006, and then do that whole thing together. So so it's 9 divided by 6, and then log that, where's log that, plus 10.64, the pH is going to be 10.82, so 3 significant figures, 10.8. Okay, so this is just a buffer calculation. Now I do want to emphasize, you may go, why is it 6 mils? That seems like a really random amount. It could be any mils, to be honest, as long as it's within the buffer region. I could change the 6 to 5.5, I could change the 6 to 7.8, 7.9, 8.2, 4.2, and you get the idea, because it doesn't matter how many mils you add, the process is exactly the same, because the only number you change is this number here, and then the process of working it out is exactly the same, because you're adding a strong acid into a weak base and you make a buffer. So you always use a buffer pH calculation to do this particular type of question, but then you just need to think about, all right, how many moles did I have at the beginning, how many moles did I add in, and then how much do I have left over, how much did I produce, chuck that into the equation, and then you'll be very happy to go with your results. Okay, so but this particular part, this particular bullet point is literally just a buffer pH calculation. Okay, so you just don't need to get confused. I see tons of people leaving the questions blank in the aqueous standard, and it just pains me to to see that, because these are very, very easy. Like if you can do a buffer pH calculation, you can do the titration curve. But going back to it, if you can't do a buffer pH calculation, then you know GG's to you. All right, and then just make sure you go back to the buffer videos and just rewatch them, practice them, and then do the titration curve. All right, this one, pH at equivalence point. So we talked about this before. This is when your pH of CH3NH2 is going to be equal to the moles of HCl. So what does that mean is that, again, you can probably see with all of these equations except the first and last one, all of the titration curve pHs in the middle, I always use this neutralization equation to show you how to do it. And I would encourage you to do that in the exam as well, because it just works. Okay, if it just works, why do you want to not to use it? Now, this is something I want you to consider. At equivalence point, it means that this and this, these two species I've highlighted, will no longer exist because they cancel each other out. So what have you produced? You have produced this and that, and we are more particularly interested in the CH3 and H3+. Okay, so let's think about this at the beginning again. So if we know the concentration, which is 0.1, the volume, which is 15 mils, which is the same thing again. Okay, 15 mils, 0.015 liters. We can find the moles, which is 0.0015. We've already done this before. Okay, so this mole for this thing is going to be 0.0015. Now that means for my HCl, I also need to add 0.0015, because at equivalence point, by definition, is when the two moles equal, because that's what equivalence point means. Now after I mix these bad boys together, this is going to be 0, this is going to be 0, and you guessed it, this one is going to be 0.0015 moles per liter. Okay, but before we do that, now we need to understand something here. We can work out backwards. We can go backwards. So if we know the mole is 0.015, we know this mole is 0.015, and I told you the concentration is 0.1 mole per liter. You can see again this volume required to reach equivalence point is also going to be 0.015 liters, because the concentrations are the same, the moles are the same, the volume is going to be the same. Okay, now in the video that I'm doing next day, not tomorrow, but the next day, is going to be exactly, well, not the same type of question, but it's going to be a little bit harder, because I'm not going to give you the same concentration anymore. Okay, so why do I need these volumes? You are going to see in a sec. Okay, so that's, just bear in mind, this is what we're doing, but just make sure that we got everything so far. Equivalence point, the two moles are equivalent, the same. We already know the concentration and the volume from the equation, so we know the mole, we know how many moles of the CH3 and H2 there are from the beginning, and equivalence moles, so that's going to be the same, but at the end, this is gone, I produce this many. So we know the mole. Now let's have a look at what we're actually dealing with here. So the only species that we have is CH3 and H3+, and then if you actually go back to the original question, it says pKa of CH3 and H3+ is 10.64. So this is a weak acid. And what do weak acids do when they are, just on their own in a solution like this? They are going to partially dissociate. So you are actually at pH at equivalence point, and I'm gonna do this in a very rainbowy color because everyone loves rainbows. Remember, this is never going to be 7. Okay, there's so many questions every single year that go, why is the pH at equivalence point not 7? Or someone go, calculate the pH at equivalence point. This is not year 11 acids and bases. Okay, you're dealing with weak acids, strong acids, weak base, strong base. The pH at equivalence point, it's only 7 when you have a strong acid and base neutralizing each other. It's never going to be 7 a year 13 aqueous, you can mark my words. Okay, so what is the pH going to be? We have a weak acid, so we just need to do a weak acid calculation. Because the strong acid and the original solutions are gone, we just need to calculate the pH of the newly produced CH3NH3+, which is a weak acid. So how do we figure out the pH? H3O plus equals the square root of Ka. Again, this equation is not given to you, I'm pretty sure, multiplied by the concentration of the acid. So we need something here. And this is the reason why this one is a little bit harder, because a lot of people just use a 0.0015 as the concentration of the acid. Well, you can't, because remember, these units, excuse me, we should put the units here. The units here are the moles. This is how many moles we have. To find out the concentration of CH3NH3+, we need the mole divided by the volume. Now this volume, well, we know what the mole is 0.015, and the volume, this is where you need to think about. This is how you need to think about how many mils are in the flask right now. Okay, so this is why I did that calculation. Initially, in our pipette, we got 15 mils. Then, to get to equivalence point, we added 15 mils. That means in your flask, you are going to have 0.03 liters, which is 30 mils. And that is why this equation, especially with some NCEA answers, they don't really explain where that number comes from, and a lot of people just get confused. You will never get it wrong if you, especially this one's a little bit easier, so this 0.03 came about quite easily. But you should always bear in mind that the number that we play with here are always mole amount. And you may go, how come? Well, if you did that, how come you didn't, this is, you used it here. You may go, you use that mole here, you use that mole here. How come you didn't divide it by the by the volume? Well, I could. I have 15 mils here. I have 6 mils here. So I could divide this number by 0.021. I could divide this number by 0.021. And what is the point? You're going to get the same number, same answer anyway. You could write it down and show, hey, I know how to calculate concentration. But the answer is not going to be any different. However, because we're dealing with the weak acid here, we need the concentration of the weak acid. We know the mole of the weak acid. We need the volume of the we need the total volume that's in the flask to get the concentration. So this is going to be just 5. I don't want to make a move for myself on the internet. Better safe than sorry. Yeah, 0.05. This is 0.05 moles per liter. So the concentration has half because it's diluted by 50%. But it's easy to see because the concentration is the same. So there we go. We got the concentration. Now we just substitute H3O plus equals the square root of Ka. What's the Ka again? 10 to the power negative 6.4 times 0.05, and then you should get an answer. I'm going to do this on my calculator. I try to get the emulator thing working on my computer. It just doesn't like it. It just keeps jumping out of the screen. So just bear with me. Get a calculator and know actually how to use it. All right, 1.06. So what's the pH? pH is going to be negative log whatever that thing is. Negative log, which is 5.97. Okay, so again, this confirms what you've done is correct because you are dealing with a weak acid, which is the pH should be below 7, never going to be a 7. Okay. Now last point. So this video is gonna titration curve is always going to be a little bit longer. That's why we need 2 parts. Now last point, to pH 25 mils of HCl is added. So let's think about this again. Yeah, we took, because we already done this part, I don't want to redo everything again. So we used 15 mils of HCl is used to reach equivalence point. Okay, because that's what we figured out in the previous question. So anything beyond 15, which is 25 minus 15, which is 10 mils, the extra HCl, these guys are the strong acid. they will, yes, you're going to have some CH3, NH2, NH3 plus, the thing that we just did, from up here. You're going to have some of these guys sitting there, but these guys are so insignificant compared to the strong acid. These guys completely dissociate. They're going to produce far more H3O plus ions compared to the, compared to these guys over here. So when we're doing this part, you're just doing a strong acid calculation. Why is that? Because the HCl is far more dominant. Okay, sounds like we're doing biology here, but it's more, it dissociates more, and we just ignore this CH3 and H3 plus. You have 100 of these, like say I always like to use a quantity number like of 100. If I already have 100 of this HCl, who cares about that one extra dude from CH3 and H3 plus? It's so insignificant, it's gonna make our calculation miserable. Let's just ignore it. Okay, so you're just doing a strong acid calculation. So we just need the H3O plus concentration. Yeah, now this is going to be a little bit tricky. So because the HCl concentration from the question is 0.1 mole per liter. All right, so that's going to be exactly the same, 0.1 moles per liter. But remember that the solution has been diluted. So the HCl, yes, it was 0.1 mole per liter, but now it has been diluted. You need to look at the volume beyond the equivalence point divided by volume, well, total volume. So it's kind of like, yes, I added 25 mils. I used 15 to get to equivalence point. So my volume beyond the equivalence point is going to be, I added 25, I used up 15, I have 10 left, which is the volume beyond the equivalence point. What is the total volume? How much did I add? I added 25 mils of HCl. What is the amount in the flask before I even did the titration? You can scroll back up, you can go backwards. It's the 15 mils from the pipette, the 15 mils of the CH3 and H2. So this is a total volume. I added 25 mils of HCl. I had initially 15 mils of CH3 and H2. This 25 is the HCl added. This 15 is how many mils of the HCl I've used to get rid of the existing CH3 and H2. And then the 10, 25 minus 10, 15, the 10 is the leftover, which is going to be the volume beyond the equivalence point. So it's 0.1 times 10 divided by 40, and this is going to be 0.025, and then the pH equals negative log 0.025, which is going to be negative log, where are you? Negative log answer, which is 1.6. And let's just use all of these numbers together. Here's what the titration curve would look like. This is the pH. This is the volume of HCl added. If we look at all of the information now, I'm teaching everything the hard way. Yeah, I'm not just going through the old exams in this particular case, because always, if you can do my questions, you can do any of the NCEA questions. Okay. The volume of HCl added. So at the beginning, oops, my bad. At the beginning, we only have CH3 and H2. Yeah. This is our initial pH. I can't remember what it was. I think it was 11.8 or something like that. This is our initial pH. When 0 mils of the HCl is added, this is our initial pH. And what it does is going to go like this. It's going to go like this. And halfway to equivalence point, at this point, which is going to be 7.5 mils, this pH equals pKa, which is 10.64. This is your halfway to equivalence point. And you may go, how do you know it's 15? Well, we used 15 mils to get to equivalence point. Half of 15 is 7.5. Okay, so this is 7.5. Now remember 10.64. So 10.64 plus minus 1 equals the buffer region. So that means approximately around here, This is going to be the buffer region. Yeah, and then your buffer is going to crash and it's going to go all the way down, and then it's going to go like that. So this is going to be equivalence point, which we calculated to be 5.97. Okay, how many mils do we use that to get there? 15 mils. How many HCl do we added? We added 15 mils to get that. Now over here we added 25 mils. What is that pH going to be? We just did it just now. 1. What was it? 1.6, 1.60, 1.06, 1.6, 1.60. So there you go. And then we added 6 mils. 6 mils was the second question just over here. You can, as you can see, within this region, this is a buffer region, and this is what I meant. You can have 6 mils, 5 mils, 8 mils, even 9 mils. Your pH is going to be within the buffer region, so you calculate it that way. Okay, so this is what a titration curve look like. I mean, it's not to scale, it's not to produce, but you get the idea. That's what a titration curve look like. And if you follow my method, you will get this right. Just always remember at each point, what are they asking you to do? What are the species that you're trying to calculate? And then just remember your equations, chuck them in, and then you do quite well. Okay, but we'll do another part in a few days. We'll do part 2, but this next time I will change the concentrations, because when the concentration are the same, it's the easiest. Okay, and then because the standard is poorly done in the nation across all the schools, they tend to keep the concentration the same just to make the calculation easier, but people still can't do it. But I'll try to challenge you. I'll change the concentration. I'll walk through this whole process again, but it's best that we can get it right the first time. Okay, so hopefully this has been helpful. Like and subscribe if you have learned anything today, and I'll see you guys next time. Bye bye.